Martin Sutherland, Institute of Therapy. Ladies and gentlemen, first I would like to thank the organizers of this symposium to give us the opportunity to talk about recent work or institute. People who did the work, I'm just talking. I will confine myself today to two subjects. First, to the behavior of nitric oxide. Second, to the oxidation of carbon monoxide. Now, these reactions are all performed on the atomic scale. I like to learn about properties of facile or demanding reactions, of structure-sensitive and structure-insensitive reactions. The field ion microscopy and field electron microscopy which we use has much more advantage than the STM, which has found so much attention recently, because we are able to identify chemically the products which we have, and we also are in the position to study the dynamics in real time. I will show you some work now on field ion mass spectrometry, atomic work. Later on, I will show you a movie, also direct, real-time, direct observation of surface-specific oscillating reactions of carbon monoxide oxidation, the second part. Now going to the nitric oxide decomposition. On platinum surface, it is well known that the nitric oxide dissociation is heavily, they have high reaction velocities on low index planes except the 111. The 111 plane of platinum is a special one, has high work function, and this might be the reason that nitric oxide is adsorbed on a platinum 111 plane in a molecular form, and we can study the dynamics of the NO on the platinum 111 plane. Now, field ion mass spectrometry, field ion microscopy, has to do with high electrostatic fields. And this one point of my message today is to show how the electrostatic field can change chemistry. I will show you that high fields act like a potassium layer on the platinum 111 plane, is able to dissociate the NO molecule, and this has been shown experimentally, and there's also some theoretical study on this project to show why the electrostatic field can dissociate NO and platinum 111. So this is the content of the first part. I will just demonstrate how we do this. First slide, please. Second slide, please. This is our experimental device. We have our platinum surface on the left-hand side. This is magnified. Actually, it's a tip which has some 100 angstrom diameter. In front of this, we have an electrode which produces the field. Now, we can image the surface at an atomic scale with atomic resolution, and we have a little probe hole here. Particles which pass through this probe hole are analyzed by time of flight measurement, so we can identify chemically what particles are desorbed from the surface. We can tilt the surface so we can have any of our low index planes facing the probe hole for mass spectrometric analysis. Using this technique, we also can use dynamic measurements. This electrode can produce field pulses, and the repetition rate of these field pulses gives us the possibility to measure the reaction dynamics. And this I will show in the next slide. We have these field pulses. Zero field, the field pulse desorbs particles from the monitor area, and then we can have a reaction time, and again, field pulse, and so on and so on. By changing the reaction time, we can measure dynamics. Either the short repetition rate, we can just get into the initial state of a certain reaction. We can look to some kind of relaxation times of the surface, and we can look to the steady state reaction time. This has been done for the NO adsorption on platinum 111. Next slide, please. We have here our platinum 111 plane. we have a continuous impact of NO, and then we have our field pulses going to this surface, so we desorb from the 111 our NO particles. Now, other than the 111 plane would dissociate, and we would desorb oxygen, N2O, nitrogen is desorbed thermally. Now, with this technique, we can measure the equilibrium surface coverage if we wait sufficient time. The reaction time, TR, is changed in this slide here from 10 to the minus 3 to 1 second, and we have, for different temperatures, measured the time which we need to get equilibrium adsorption, and with different temperatures, the intensity of the coverage of the NO equilibrium concentration changes, and if we put this in radius plots, then we can find the activation, the binding energy of the NO to the 111 plane, or the heat of desorption of NO, neutral NO to the surface. And you can't see this, but here, write down data for the frequency factor and for the energy, and we can compare these results with molecular beam studies. I will not go into detail. This molecular beam studies, this pulse beam, and again you can get this energy of NO absorption, which is the same value which we find for our field pulse techniques. No, it's fine. So there is a possibility to combine other techniques and to find the same data. Next slide shows you how our electrostatic field changes the what we are doing here is just changing our reaction fields if R. So we continuously change the base field of the field pulse experiment. So we can choose different field strengths to have the reaction of the NO molecule with the surface. The field strengths can be measured with an accuracy of 2%, so we can use the field strength as a reaction variable. And this has been done in the next slide. Slide. No, go back please. The field strength FR varies from 0 to 12 volt per nanometer. 12 volt per nanometer, 1.2 volt per Angstrom. You see that the molecular adsorption of NO, left-hand side, the NO is getting to be unstable at a certain field strength. 0.4 volt per Angstrom decomposes, and you can find N2O, nitrogen, and oxygen. Now this is a rather curious reaction, and former considerations of the influence of electrostatic fields in terms of polarizabilities, in terms of interaction, field interaction with molecules in the Markov equation, that you can define an electrical momentum of a reaction, do not apply, because the dipole moment of the NO molecule and N2O molecule, they are higher than the zero dipole moment of oxygen and nitrogen. So field influence would always reverse the reaction and find that they have a NO decomposition. And this has been calculated by quantum chemical aspect by Jürgen Kreuzer. Next slide. So this shows the electron distribution in an NO molecule at zero field. We find by this calculation by Kreuzer and Wang, it's an extended Hüppel calculation which has the electrostatic field superimposed to the electronic system, and one can see how the electron distribution shifts due to field influence. The oxygen I have to say that the metal nitrogen bond strength is decreasing by electrostatic field and the molecule can tilt. Only a tilted molecule then can dissociate. One can measure, next slide please, or one can calculate the charge transfer during the tilting angle at different field strengths and can calculate an activation barrier, next slide, for the dissociation of the NO molecule to nitrogen and oxygen. And also, next slide, one can calculate the formation of N2O when the nitrogen atom switches into the NO bond. This has been published in Surface Science. I will not go into detail because we have some other things to discuss. The NO bond energy has been measured recently on platinum or rhodium surfaces. And again on fines. This is the desorption field strength on the NO molecule on a rhodium surface. The equilibrium concentration MnO has again been measured at certain reaction times, and we have the equilibrium and the temperature dependence has been evaluated at I have to learn. So this is a field strength on the rhodium 111 surface, and the binding energy which shifts from about 110 to 97 kilojoule per mole, and the again the available data by Kreuzer show that they have a shift which is nearly what we expect from our experimental work. So, to summarize up this part, we can say that this field ion mass spectrometry with atom probe work, it's possible to look on a surface area and to see how molecular dynamics, binding energies, how the decomposition of surface compounds occurs under external conditions. We can also measure field influences on these processes. Another possibility to look into the surface specific of reactions is to do with field electron emission work. And could I have the next slide? This is okay. Here, this is the oscillation of the carbon monoxide oxidation on the platinum surface. Now, platinum is known to be very specific in oscillation reactions. This no again means no. Oscillations shows platinum 111. Again, the surface with the highest work function. For the 001, we have oscillations between 480, 530 Kelvin under certain conditions of pressure. Also for 011 platinum, the conditions are different, but they are very precisely. It has to meet these conditions very precisely in order to observe these oscillations, because these oscillations have to do with the bistability in the absorption system of platinum. Next slide. Yeah, this one shows how we can explain or understand this special behavior of the platinum surfaces in respect to oscillation reactions. the production of carbon dioxide. In 1 minute we have the carbon dioxide formation depends on the carbon monoxide pressure at constant pressure of oxygen. The oxygen pressure is always 1 order of magnitude higher than the carbon monoxide pressure. At low carbon monoxide pressures we have a first order reaction. Then we have a point where the carbon monoxide surface coverage is overwhelming. The reaction rate drops to 0 or low values because the surface is poisoned by carbon monoxide. By a reaction which is not very well disclosed, the carbon monoxide can be, maybe by subsurface oxygen, reduced, coming back to the point of low carbon monoxide coverage, higher oxygen coverage, and we again have a high reaction velocity. So the oscillation is always around this bistability point. And now the surface of such a platinum emitter can be imaged by the work function. The carbon monoxide covered surface has a rather bright appearance because relatively lower work function, higher emission current, and the low oxygen surface has a less emission, higher work function, and this can be seen in the field electron emission images. Could be seen in the video. This video has been shown already in Budapest, so excuse for those who have seen this, and maybe focus a little bit if possible.
It's a lighthouse.
Can we? Yeah, okay. These are the oscillation conditions. We have 3 different tips. One is 1100 angstroms, 111 oriented. Then we have a 001 oriented and the 012 oriented tips. And these are conditions. I have to say the temperature is always constant. This is a field ion image of the 111 oriented tip. This is the 110 surface. And this is the surface where we will have, this is the starting oscillation. This is the oxygen covered surface. We do nothing, just wait. Suddenly, this is the carbon monoxide process. It is reduced, and quickly, again, carbon monoxide will be covering the surface. We have measured the propagation of the propagation wave of the oscillation. I can show you. We also have measured the work function of these planes. Again, carbon monoxide covered, heating up, oxygen covered, constant temperature within tenths of a Kelvin, and real time. Real time. Again, oscillation, the resolution, spatial resolution is 20 angstroms. Still the 101 oriented tip. This video has been taken by Dr. Gorodets. We will move over to another, to a 100 plane, it's here about, and we have switching on. This one now, this one will come. This is the disturbance of the channel plate. And we will have another one coming here. One has to say something about, because these 110 planes which are switching on here usually have information about synchronization by gas phase communication, but on the emitter tip this doesn't work. We will have a local oscillation around this 011 plane. We will have a bright 331 plane, which will have a local oscillation. There will be no oscillation at this point. The total length of this video is 300 seconds, so we are half this. There will be a oscillation starting right here about this area.
Johan, could you tell us in the meantime, how did you perform the experiment? You pre-absorb oxygen, maybe at higher temperature to
we have always steady flux of oxygen and carbon monoxide.
Oh.
Nothing is changed. We have a constant proportion of oxygen and carbon monoxide.
And the temperature of the
The temperature of this tip is about 440 Kelvin.
You
It is stable within a tenth of a Kelvin about. So we will have oscillation coming here. This is a self-organization of an absorption system. So we don't do anything from external parameters. The internal parameters are such that this bistability point is reached, and we come from oxygen to carbon monoxide, carbon surface, due to internal reactions in the adsorbed layer. So nothing, the external parameters, which are temperature, partial pressure, flow rate, they are all constant. We don't do anything. But the oscillation,
even during the reaction, the temperature was 1.5, there is no reaction heat or...
the heat of the reaction is so small that it wouldn't change temperature.
And you use a channel plate to take the picture of the whole
This is a channel plate, and we have a very low field and a low emission current. The low emission current is about 1 nanoampere. But we have a high magnification by the channel plate. This is a 012 plane, and we see oscillations. This is a carbon monoxide wave, oxygen wave, carbon monoxide wave, oxygen wave. There is a lot of information in these pictures which I can't explain right now. The carbon monoxide wave is diffuse. The oxygen wave is very strict. So this has to do with kind of fractal behavior of this system. The 102 plane, oxygen side, carbon monoxide is coming slowly. Now if we at one point change a little bit pressure, the oscillatory behavior is completely changing in frequency and amplitude. We have done this here. I think this may be the higher pressure already.
But there are certain parts of the tip which are much more active. Probably you could tell us which phase of the most active on different sides.
Oxygen and carbon monoxide layer. The propagation rates have been measured. The time resolution of these images is about 40 milliseconds, and the fast switch-on reaction where we saw the carbon monoxide immediately coming to the surface is this one here. And the waves of oxygen is the smaller one. So one can measure these. It's about 5,000 angstroms per second, which the carbon monoxide moves. One can put this into relation to surface diffusion and things which I have no time to discuss this, but there's a lot of other material inside. I have used up my time, more than my time. Thank you very much for your attention. Thank you.
Papers now open. We have only 1 minute and a half. Please identify yourself.
It seems to me that there are at least 2 interactions of chemical molecules in its dissociation. First, this interaction with the surface, may I call it a chemical interaction. Secondly, this interaction with the electric field. What is the dominant effect in its dissociation?
Now, you have to ask which field you are in. The electron emission was in the field of about 1 volt per nanometer. And the field desorption of NO was about 1 volt per angstrom. That's 1 order of magnitude difference. In temperature, you are familiar. If you say, I have a reaction at 100 Kelvin, you would imagine that a reaction at 1000 Kelvin would be different. The same applies for field. A field of 1 volt per nanometer. doesn't make much, but a field of 10 volt per nanometer gives a lot of chemical changes. So the dissociation of NO is at these high fields, higher fields, and the reaction of carbon monoxide is at the lower field. We have no indication so far of field effect.
Thank you again.